As we've seen in the previous three videos, when we are trying to make examples of groups that come from the world of matrices, the computations can kind of get intense if we do not think about things that we know from linear algebra. So in this video, what I want to do is I want to look at a list of topics from linear algebra that you really need to know in Math 301. We're not going to prove any of these topics. The proofs of them belong back in that linear algebra course that you should have taken when you were a sophomore. On the other hand, if you don't remember these things, you really need to go back through your linear algebra notes and relearn this material. So without any more ado, let's go ahead and get started. The first thing that you really need to know from your sophomore linear algebra course is you do need to know about matrix arithmetic. And what I mean by this is you really need to be able to add and multiply compatible matrices together. You should also know about scalar multiplication. The second thing is that there is a really big theorem that is part of matrix arithmetic, but this one is one that I do want to kind of highlight as a theorem that says matrix multiplication is associative. And what this means is that if A, B, and C are compatible matrices, if you look at A times BC and you look at AB times C, they are the same thing. We looked at a special case of this in the second video on the set of videos for GL2. But the general proof that matrix multiplication is associative is usually done in a very different way. And if you don't remember it, I do have some links on my Blackboard page that give you links to 3 videos from Khan Academy that prove that matrix multiplication is associative. But that's a really big theorem, and you need to know that it is there. The third thing that I want to put on my list of important facts is that you need to know about the identity matrix. And the identity matrix, we have one of each size. IN is an n by n matrix that looks like ones on the main diagonal and zeros everywhere else. And this is called the n by n identity matrix. And there, like I said, there's one for each size. Just to be kind of quick, I3 would look like this. I4 would look like this. Let's see, continuing our list of topics. The fourth thing that I want you to know is that the identity matrix is always a right identity element when we are dealing with the set of n by n matrices where their coefficients are pulled from the real numbers. So this set is the n by n matrices with real entries. And what I mean by IN is always the right identity is pretty simple. If we have A is an n by n matrix, then it turns out that A times IN will be A. The fifth thing that I want to talk about is the formal definition of an inverse matrix. If A is an n by n matrix, and there exists a B that is also an n by n matrix, such that A times B is equal to that identity matrix, then we call B the inverse of A, and we write B is equal with a -1 subscript, and this is read as A inverse, so we read this as A inverse. It's important to note in this particular definition that A and B are both square matrices. The next fact that I want to review with you is a set of important theorems about inverse matrices. So, theorems about matrix inverses. And the first one says that A inverse exists if and only if A itself row reduces to the identity matrix. The second theorem says A inverse exists if and only if the determinant of A is not equal to 0. Now, it's important to understand that, and I'm going to throw this on as a seventh idea, the determinant of A is a function that takes n by n matrices into the real numbers. In other words, det A goes from the set of n by n matrices to the real numbers. And there are several important properties about the determinant. We're not going to get a whole lot involved in all of them. What I want to do is I want to say there are usually two standard ways to calculate det A for matrices that are larger than either 3 by 3 or, well, either 2 by 2 or 3 by 3. So I'm just going to leave it as 3 by 3. There are the two standard ways of calculating determinants for matrices that are larger than 3 by 3s are what is known as cofactoring along a row or a column, or there's another way that involves row reduction. It doesn't really matter if you remember that much about computing determinants. I just want you to have this idea that this function is out there. There is one more thing that I want to think about in terms of determinants, and that is how to compute a determinant of a 3 by 3 matrix. And rather than doing that here, let me go to the next board. So 8. Computing a 3 by 3 determinant through what is often called basket weaving. And if I have a determinant, and I'm just going to call it A, B, C, D, E, F, G, H, I, the determinant of this 3 by 3 matrix can be found, and I'm going to use my marker for showing stuff, but it can be found in the following way. The first thing is we're going to look at the product of the main diagonal, so that is AEI, plus, then we're going to look at the product of this thing, which is called a diagonal, BFG. And then we're going to look at a final positive diagonal, which is made up of C and DH. And then we subtract off 3 negative diagonals. First of all, we've got this negative diagonal, the main negative diagonal. So we're going to subtract off CEG. Then we're going to subtract off this times that. So that would be minus BDI. And then finally, we're going to subtract off A times that pair, FH. And at some point, you were probably shown this basket weaving method of computing determinants. I'm not going to do an example. You can play with this formula, and I'll have you do one of them on a quickly jot. The final thing that I want to review from linear algebra is an important theorem about determinants. And this theorem says that the determinant of a product is the product of the determinants. Now, if you think back to the videos on GL2, at one point we proved this for 2 by 2 matrices in one of those videos, but it generalizes to all n by n matrices, that the determinant of A times B is the determinant of A times the determinant of B. You will need to use these theorems in class next time to prove some things about certain sets of n by n matrices.